Okay, so we talked a minute ago about being able to graph a complex number on the complex plane. And we've got a real axis and we've got an imaginary axis. If you think about what we did in the last section, it shouldn't surprise you too much to realize that we can think about imposing a circle on this axis. Pretend that that's the right diameter. And if we do that, then we can talk about the location of this point in polar form, right? Because I've got a radius and I've got a theta. And in fact, it turns out that we can indeed do this because if we think about the coordinates of this point, they're 3, -4. And so we know from our previous work that the x-coordinate, which is A, is equal to r cosine theta. And the y-coordinate, which is B, is equal to r sine theta. And we know that a squared plus b squared equals r squared. So we can write an imaginary number, z equals a plus bi, as r cosine theta plus I r sine theta, where a squared plus b squared equals r squared, and cosine theta equals a over r, and sine theta equals b over r. So let's take the number we've got right here. Let's express 3 minus 4i in polar form. Okay, so a equals 3, b equals -4. If I do the work, I can get to r equals 5 fairly quickly. 3, 4, 5, that's a Pythagorean triple. You can get there from a squared plus b squared equals r squared relatively quickly. So we've done this before. We did this with this point in the Cartesian coordinate plane, right? So we know r equals 5. That means that we know that the cosine of theta is equal to a over r, which is 3/5. So theta equals the inverse cosine of 3/5. Or remember that theta also equals 2 pi minus that value, because inverse cosine only gives us the top half of our unit circle. So let's use Desmos. We're always going to do this work in radians. So the inverse cosine of 3/5 is 0.9273. Take 2 pi minus that. 5.3559. You want the fourth quadrant value, which is this one. And you can check that by taking the sine of 5.3559 and multiplying that by 5, and we should get something close to 4, -4, and we do. So what we know now is that we can write the number 3 minus 4i as r cosine theta. So 5 times the cosine of 5.35559 plus I times 5 times the sine of 5.35559. Now that's not really very helpful yet, because that is still a complex number, right? But there's a thing called Euler's formula. And this is where things get really interesting, because Euler's formula, and really useful, Euler's formula says that r cosine theta plus IR sine theta can be easily rewritten as r times e to the I theta. I'm not going to prove this. Your textbook doesn't prove this. We are just going to accept it. This is where things get really interesting. Because what it means is that we can take this number z equals 3 minus 4i and write that as 5 times e to the 5.3559 I. Okay. This is rectangular form. This is polar form. Why in the heck would we want to do that? Well, before I answer that question, I'm going to do another video with converting back, that it demonstrates a few more times converting back and forth between polar and complex form.